Okay, welcome everyone back to the second lecture of this workshop about electronic optimization. Let me introduce today's speaker is Martijn Marsman, who has been developing VASP for more than 20 years. Martijn contributed to many of the advances in VASP, from hybrid functionals and beyond DFT methods to constraint moment calculations. Recently, one particular focus of his work has been to make VASP fit for GPUs to take full advantage of their performance. In this lecture, he will focus on some of the core algorithms that allow VASP to determine the electronic ground state. Martijn, please take the stage.
Okay, thank you, Martin. So, hi everyone. My name is Martijn Marsman, as Martin mentioned, and I'm working as the head of development for the VASP software company. And today's lecture is about electronic optimization. So a rough outline of what you can expect of this lecture is shown here. So we'll first state the problem that we're trying to solve. So quickly go over things like total energy, Hamiltonian, Cohen-Sham equations. And then we'll discuss a category of methods of electronic optimization called direct minimization. And that will lead us to discuss a problem that these optimizers face, and that many optimization methods face, and that's the problem of charge sloshing. So we'll discuss this. And then we'll discuss another category of electronic optimization methods, the self-consistency cycle. It's designed to deal with charge sloshing. And the self-consistency cycle consisting of diagonalization and density mixing. I will have a look at these two components separately. So first density mixing and then a matrix diagonalization. And the second part of this lecture is a bit heuristical and contains of tips and tricks and do's and don'ts and answers to frequently asked questions concerning electronic optimization and convergence of those methods. So let's look at what we are trying to do. So what we are trying to do is to minimize the Cohen-Sham free energy. Well, here it's shown for a DFT. The Cohen-Sham free energy consists of the sum over the Cohen-Sham orbital energies minus double counting corrections. Those are shown here. Hartree energy, depending on density, exchange correlation energy is added, and the action of the exchange correlation potential on the density is subtracted. So this gives you the, and there's a third term, and that's related to partial occupancies to deal with metallic states, and this is the entropy, electronic entropy. The electronic density, so this energy is a functional of the density, and this electronic density in Cohen-Sham density theory is computed from the Cohen-Sham orbitals in the manner that is shown here, so from the occupancies and from the orbitals. And so those occupancies are functions of the eigenenergies. So in the end, what we need to be able to compute this thing, this free energy, is Cohen-Sham orbitals and eigenenergies. And these orbitals and eigenenergies are solutions to the Cohen-Sham equations, as written here. And there's an eigenvalue equation that is solved under the constraint that the orbitals are S orthonormal. As you see here, the Hamiltonian, we don't go into the details of it. So this we use this PAW method, so it's a certain Hamiltonian, but it's a function of the density. And as we see here, the density depends on the solution to this equation. So it's a self-consistent problem that we need to solve. So as I mentioned before, there's two categories of methods of electronic optimization implemented in VASP. The first category is the category of the direct minimizers, and the second category is the methods that are the self-consistency cycle. So the first category, direct minimization, and there we start with building in the orthogonality constraints into the functional that we minimize. So we have here, these are Lagrange multipliers that essentially enforce S orthonormality of the orbitals. So those are added as as Lagrange multipliers to the free energy functional that we have. And then here there's another Lagrangian part, and that essentially forces the sum of the occupancy numbers. And the sum of those occupancies should add up to the total number of electrons. That's essentially what those two things do. And so in direct minimization, we directly minimize this Lagrangian with respect to the orbitals. And to be able to do that, we need to we need to use the gradient of this Lagrangian with respect to a given orbital. And that is written down here. I've left out the part of the gradient that stems from this. I will not deal with that here. For the things that I'd like to discuss, it suffices to take these parts of the gradient. And what we see here is two things. First of all, we see that essentially the gradient is obtained by applying the Hamiltonian to the current orbitals. And that is what this is supposed to show you. And we have split it here in two parts. And the first part is called, that is this part, the first term on the right-hand side. This is called the out of subspace part of the gradient. So if we say, okay, the gradient is essentially the action of the Hamiltonian on the orbital, and then we project out the space that is spanned by the current set of orbitals. So the current subspace is projected out. So this is the out of space part of the gradient, out of subspace part. And then there is a so-called subspace rotational part of the gradient. And that is determined by the Hamiltonian expressed in the basis of the current orbitals, so within the current subspace. So from this gradient, we can derive search directions. So search directions are actual changes of the orbitals along the separate parts of the gradient. And commonly, this is done in the following way. So for the out of subspace part, it's essentially the gradient times a preconditioning matrix. It's shown here. So a preconditioned gradient gives you the search direction. And the subspace rotational part is a unitary transformation of the orbitals that span the current subspace, and a small step along that gradient can be derived from Loveday perturbation theory and is shown here. And it essentially depends, as you see, on the off-diagonal elements of the Hamiltonian expressed in the current subspace. Those are perfectly valid search directions, but we use a slightly more sophisticated method in VASP. And it's based on the work of Vrijsold. I will not go into the details of that. If you're interested in that, there's a paper on it that one can study. One point to be made, of course, there are three components actually, three components to the gradient and three search directions. Like I said before, out of subspace gradient and search direction, a subspace rotational part, and then of course associated with this term that I didn't want to discuss, there's also a search direction for the partial occupancies. So if one has these search directions, and you can read the paper of Vrijsold if you want to know how they are constructed exactly, but let's suppose that we have those search directions, then we can use conjugate gradient approximation or a damped molecular dynamics scheme, a damped velocity friction algorithm to optimize, to minimize the Lagrangian with respect to the orbitals. So to change the orbitals in such a way that the Lagrangian is minimized. And we do this, so we continue to make steps, to make conjugate gradient steps or damped molecular dynamics steps until this Lagrangian, or the total energy, if you so want, the change in this total energy, the absolute change in this total energy from one step to the next drops below a threshold that the user provides. And at that point, we say, okay, we're done. We're finished with the optimization, and we have reached the electronic ground state. So in every iteration, the orbitals are changed, and the charge density is recomputed, and total energy is computed, and a new Hamiltonian is constructed. So that happens in every step. in every iteration. So this sounds like a very neat scheme to deal with electronic optimization, and it is in a way. Only for metallic and small gap systems, this scheme tends to suffer from a phenomenon called charge sloshing, and we'll have a look at this now. So this is a very hand-waving illustration of the phenomenon of charge sloshing. Let's suppose that we have a system that consists of two atomic sites, chemically identical atoms. And at some iteration during the process, these are the levels, electronic levels associated with the sites. It's very hand-waving. And at some iteration, the lowest level on site 1 contains 2 electrons. And in this situation, actually the lowest lying electronic state, one electron state at site 2, lies below the one on site 1. So what will happen is the charge will be transferred from one side to the next. And that is illustrated here, and is also illustrated what, if you're unlucky, what then might happen. So 2 electrons have been transferred from side 1 to side 2, as shown here. And now this level ordering has reversed. All of a sudden, these levels have gone up and these ones have gone down. So in the next step, the charge will be transferred back. And if you're very unlucky, then this will happen. It was just ping pong between these two situations. And the actual ground state will never be reached, because that would, in this hand waving example, that would be this situation. So that in a nutshell is charge sloshing. So this is a very hand waving picture, but in fact, we have a nice example here where you see this illustrated by means of an actual charge density. This is an elongated supercell of iron, and it's slightly disordered, so that there are no symmetry equivalent sites here. And what we see here is the change in the charge density from one step to the next along the iterative path. This is, I think, iteration 54 and 55 using conjugate gradient. And what we actually see, if you assume that the yellow is plus and blue is minus, and then we see from step 53 to 54, charges increased here, and it has been removed from here and from here. And in the next step, we see the situation essentially reverses. Not exactly, of course, but you get the picture. And in fact, this particular calculation, so this disordered iron in a fairly large cell, will never converge with the conjugate gradient method due to this charge sloshing. So a more mathematical description of this we'll go through here. So where does this come from? We've looked at this gradient. We saw that there's 2 parts, a out of subspace and a subspace rotational part to the gradient. And I'll show you here that's actually this part of the gradient, this subspace rotational part of the gradient, that is prone to charge sloshing. And this is also quite a bit hand waving, but a little bit more mathematical than what I showed you before. So let's consider that we have 2 states, free electron-like states, and one is slightly below the Fermi energy and one is slightly above the Fermi energy. In that case, a small subspace rotation, so this a small step along this part of the gradient will take the form that you see here. So it's a linear combination of the original orbitals that we have. Step size is chosen here to be delta S, and essentially a little bit of psi m is added to psi n to yield psi prime n, and a little bit of psi n is subtracted from psi m to yield psi prime m. Now these are small changes in the orbitals, and what they mean for the charge density is shown on this right-hand side panel. So a small change in these orbitals leads to a long wavelength change in the charge density. That's shown here, right? So the wavelength here is this delta K, which we suppose is small. So it's a long wavelength change. And the bad news is that these long wavelength changes in the charge density are strongly amplified in the response that they yield in the electrostatic potential. And so we see here that this long wavelength change is hugely amplified because we divide here by delta K squared. And if we would iterate such a scheme, then the stable step size for a simulation box with largest dimension L, so we had this elongated cell of iron, so the L was this large dimension of that, then we see that delta K in this picture is proportional to 1 over L, and the response in the potential is then proportional to the square of L. And the stable step size is then actually smaller than or proportional to 1 over L to the power 2. So we need to take exceedingly small steps to still have a stable algorithm. And yeah, in practice, we don't reach convergence with this. So what do we learn from this? Charge sloshing occurs when we have states slightly above and slightly below the Fermi energy, but close to the Fermi energy. So metals and small gap systems are prone to charge sloshing. And charge sloshing is a more of a severe problem when the simulation box becomes large. And what we also learned from this is that it's essentially not limited to a hopping from one side to the next. If you saw one side, it doesn't necessarily have anything to do with localized electronic states. Okay. Good. Here we see an example. So this line you see here is this is the change in the total energy with respect to the ground state. Oh, sorry, this is the difference between the total energy and the ground state energy for this disordered iron cell with eight cells. I said, right? So, and this is conjugate gradient, right? So it converges exceedingly slowly. We see that for the longest cell, which is 8 of some units, it converges the worst, slightly better, but still very bad for a cell that is half as big. And for one that is 8 times as small, we see, yes, actually we can reach convergence. So this illustrates that indeed it's the cell size is a very deciding point in this, how badly a system is affected by charge sloshing. Okay, so what can we do? This brings us, in fact, to the second category of electronic minimizers, and that is this the self-consistency cycle. In the self-consistency cycle, electronic optimization is divided in 2 sub-problems. The first sub-problem is refinement of the wave function, so determining the eigenstates and eigenenergies of a given Hamiltonian. And keyword there is matrix diagonalization. And the second sub-problem is refinement of the charge density. So how do we construct a new charge density out of, if we diagonalize this matrix, we get eigenstates, we get a new charge density, and we went in with a certain charge density. After diagonalization, we go out with a different one. So how do we, out of those two, how do we construct a new charge density for the next iteration in a way that avoids charge sloshing? And that is this, the keyword there is density mixing. So the whole scheme would go something like this. You start with a trial charge density, and normally in VASP those are overlapping atomic charges, and trial wave functions, simply filled with random numbers. And for this initial charge density, you set up a Hamiltonian. Now you determine the eigenfunctions and eigenenergies for this Hamiltonian, and those give you new partial occupancies and a new charge density. Then you take the charge density that you went in, so the initial one and the one that comes out, and you use that to construct a new charge density. And that new charge density gives you a new Hamiltonian, and the whole thing starts all over again. You diagonalize that one, you find eigenfunctions, and so on and so forth. And you do this until the change in the total energy drops below a certain energy threshold. Yeah, that's essentially how this works. Since we went in with the idea to solve this problem of charge sloshing, I will first have a look at this particular sub-problem of the self-consistency cycle, density mixing, because this addresses essentially the problem of charge sloshing. So from linear response theory, we know that a change in rho in with respect to the self-consistent charge density that we're seeking, right? A change of rho in with respect to the self-consistent charge density leads to a change of rho out with respect to this self-consistent charge density that is given by this proportionality, where chi0 is the polarizability in the independent particle picture, and nu is the kernel of the Hartree interaction, and FXC is the derivative of the exchange correlation potential with respect to the density, with respect to changes in the density. So with this, we can see that the self-consistent charge density that we are seeking is essentially given by what we call the residual. So the difference between rho out and rho in plus rho in. Epsilon to the -1 times this residual. And epsilon to the -1 is the so-called inverse of the microscopic dielectric function, and it's given by this expression. And this is in literature, you'll find this denoted as j to the -1 for whatever reason, and there it's often called the charge dielectric function. So in the old literature on density mixing, that is. So if we would know the inverse microscopic dielectric function, then obviously once we have one residual, so we start with rho in, we get a rho out, we can compute the residual, and then if we knew epsilon to the -1, we essentially could, our mixer could tell us that the self-consistent charge density is this. We would reach it in one step. And unfortunately, we do not know epsilon to the -1 a priori. So what we do is we use a model dielectric function. And that is a good approximation, a good initial approximation for most systems. And that's taken from the work of Kerker on density mixing. So epsilon to the -1 or j to the -1 is given by this model. You see it depicted here. Yeah, so A min is this little bit here, and then there's a dependence on the wave vector of the charge density. Yeah? So components of the charge density in the reciprocal space. And there's a linear mixing factor here, that's this A mix. So these are, by the way, the defaults that VASP uses for this function. So this is the initial approximation for the charge dielectric function. And then we use a mixing scheme. In fact, it's a Poulet mixer or a so-called modified Broyden mixer. We use a mixing scheme that we start with this initial approximation to the inverse dielectric function. But this mixing scheme refines this approximation. So it learns, if you so want, it learns the dielectric function from the history of the combinations of rho out and rho in that it sees. So as it mixes, it approximates this function ever more finely. Yeah, so if you're interested in this, the literature on the Poulet and modified Broyden mixer are denoted here as well. Yeah, so the defaults, like I said, the defaults for this Kerker-like function are given here. So those are these parameters: A mix 0.4, B mix 1.0, A min 0.1. So this is this particular function. Then the history that is taken to learn the approximation to the charge dielectric function, the size of that history, so how many steps of charge density will the system keep in memory to learn this relationship, that is given by max mix. And then there are a few other parameters that one might play with. We'll come to that a little bit later. So what does this do? This maybe also a point that I should stress. So essentially what you see here is that what it does is that it will suppress changes at small g, so at long wavelength. Changes of the charge density at long wavelength are suppressed by the mixer. And that is essentially what you would expect to help against charge sloshing. So that's one part of the scheme. The second part of the scheme is matrix diagonalization, so refinement of the wave functions, matrix diagonalization. So let's take a step. So a naive solution to this problem would be the following. And one could express the Hamilton matrix in the plane wave basis and then simply diagonalize it. And so we have, well, you have heard this in a previous lecture, I hope, about the plane wave basis set and the criteria that determine its size. Well, we can express the Hamiltonian within this basis. So it's a matrix of G and G prime. And then we diagonalize it and we get NG, so the number of basis vectors, solutions, eigenstates, and eigenvalues to this problem. So why do I call this a naive solution? It's naive because we do not need so many solutions to the Hamiltonian. We do not need so many eigenfunctions to the Hamiltonian. So for ground set calculations, we only need the lowest eigenstates of the Hamiltonian. In fact, we need a number that is of the order of the number of electrons in the unit cell. We need as many orbitals that so that we can populate them with our electrons and compute the density. And we do not need a whole bunch of high-lying eigenstates at high eigenenergies. So because this NB is, as a rule, much, much smaller than NG. And matrix diagonalization scales with n to the power 3, so cubically. So exact diagonalization scales badly with this number, if you so want, right? So we are doing, if we diagonalize this exactly, we do a lot of work to get solutions that we in fact do not need. Now, the way around this is to use iterative matrix diagonalization techniques that allow you to compute the lowest eigenvectors of the Hamiltonian. And those are RMM-DIIS and the block Davidson. Those are the ones that are implemented in VASP, the ones that I will discuss. So before we get to that, let's have a look at the key ingredients that are used in all iterative matrix diagonalization schemes. So those key ingredients are Rayleigh-Ritz optimization and the residual. And Rayleigh-Ritz optimization is a diagonalization of an n by n subspace spanned by the current orbitals. So like the Hamiltonian within the basis of our current orbitals, or of a set of orbitals, and the overlap matrix. And we can solve this eigenvalue problem within this n by n subspace. And that will yield a bunch of eigenvectors, linear combinations of this set, and approximate eigenenergies. And these states actually are the best approximation to the exact eigenstates of the Hamiltonian within the subspace spanned by the current orbitals. So that's Rayleigh-Ritz optimization. And the residual of an orbital is this, it's written here. So essentially it's a measure for the deviation of such an orbital from being an eigenstate. Because if it was an exact eigenstate of H, then this would be 0, right? Okay. So block Davidson uses those ingredients in the following way. It takes a block, a set of all our orbitals that we are trying to determine. So this is the complete set. It takes a subset of this, and then it extends this set by adding the preconditioned residual factors. So here you see these are the vectors of the set. And this is the residual of those. This is preconditioning. Now let's forget quickly about this. But this preconditioned residual of psi 1 is added to the subset. And within this 2n by 2n subspace, we do a Rayleigh-Ritz optimization. And we take the n1 lowest eigenvectors of that optimization. Those are then added again to the subspace. So we take those solutions, compute the residual, and add them to the subspace. Now we have a 3n by 3n subspace, and again we do a diagonalization and take the lowest n eigenvectors of this diagonalization, and so on and so forth. Now, if you continue doing this, if you continue increasing the subspace this way, at some point, the lowest eigenvectors of this Rayleigh-Ritz optimization will be exact eigenvectors of the Hamiltonian. Now, in practice, we do not do this indefinitely until they're completely exact. We do this, I don't know, we go to iteration depth of 4, so we extend this to until we reach a 4n1 by 4n1 subspace. Once we've done that, or until some other break-off criteria is met, then we replace the original orbitals by the optimized one, and we move on to the next block of orbitals out of this. Yeah. So when all orbitals are updated, a diagonalization of the full subspace is done. So one single diagonalization of the full subspace spanned by the current orbitals is performed. So this is actually the worst scaling step. This scales cubically, like I said before, and of course this is the total number of orbitals. So this is the worst step that we do, but it has normally you don't see the effort compared to what is the rest of the effort in the Davidson algorithm, because the prefactor is smaller. So the block size used in the Davidson algorithm is set by a tag, NSIM tag. Normally you don't need to set it, but if you would like to do so, you can. In principle, N1 is 2 times NSIM, and for technical reasons, however, it needs to be divisible by a particular integer, and this integer is related to the parallelization of the problem over MPI ranks. If you're interested in this, please read the wiki section on the parallelization basics. This is this integer. Like I said, normally not something that one would need to tune. So the break-off criteria, so how long do we iterate a certain block of bands before moving on to the next? Well, like I said, maximum iteration depth is normally set to 4. Or we might stop optimizing orbitals because certain convergence thresholds have been reached. They may be fine-tuned by means of these parameters. They are related to the size of the residual, the change in the eigenenergy of an orbital from one step to the next, and so on. We do not recommend that you play with these parameters, but rather rely on the defaults. So the block Davidson is approximately 1.5 to 2 times slower than RMM-DIIS, but more robust. So let's move on to RMM-DIIS. So RMM-DIIS works in the following way. So if we want to optimize a certain orbital, we start by computing the preconditioned residual of that orbital. Now that I've written here, so this is the residual, this is this approximate eigenvalue, it's a preconditioning matrix. And as a first step, we take a Jacobi-like trial step along this direction of the preconditioned residual that's shown here. So it's this trial step lambda. And we compute the residual of this new orbital. And then we seek a linear combination of psi0 and psi1, a linear combination, in such a way that the residual factor is minimized. So the residual factor is computed as a linear combination. So we assume that the residual is linear in the residuals of psi1 and psi0, in the same way that this linear combination is taken here. And we want to minimize this residual. This means that we have to minimize this expression with respect to these parameters alpha I. This is called the direct inversion of the iterative subspace. Now, once we've done that, then the second trial step, M2, starts from psi bar 1 along the direction of this residual that we have minimized. And with each iteration, M is increased by 1, and we add a new trial orbital and its corresponding residual to the iterative subspace. And so this problem becomes larger and larger, if you so want, this minimization problem. And we iterate this until the norm of the residual drops below a certain threshold, or we have reached the maximum iteration depth. Once we have done that, we replace this original orbital by its optimized one, and we move on to the next orbital. So this trial step size is one thing that I've not talked about yet. It's critical for the stability of the orbital. And as a reasonable approximation, we optimize the trial step in the first step by minimizing the Rayleigh quotient along the search direction with respect to lambda. And then we use this lambda for all further trial steps until we move on to the next orbital. The break-off criteria, so the optimization stops when either the maximum number of iterations per orbital has been reached, this is per default also 4, or a certain convergence threshold has been reached. Like I said, size of the residual drops below a certain break-off criterion, and so on and so forth. Those are again given by these tags, but we do not recommend you optimize your problem with respect to that. So the good thing about RMM-DIIS is that it works completely on a per orbital basis. And as such, it parallelizes trivially over orbitals, which is good. To cast some of the operations into matrix-matrix multiplication form, we work on batches of orbitals simultaneously. A drawback of the RMM-DIIS method is that it always, if you optimize a state, it will always converge to the eigenstate that is closest to it. So in principle, you will converge to those states that are spanned by your initial orbitals. So you need to have a way of constructing good initial orbitals before you can rely on RMM-DIIS. Otherwise, it might miss certain eigenstates. So to avoid this, we either use the Bloch-Davidson algorithm to construct the trial orbitals. The trial orbitals are essentially filled with random numbers, and then we do a few steps of Bloch-Davidson optimization of them to get reasonable orbitals, and then RMM-DIIS kicks in. That is what you get when you use algo is fast. If you use algo is very fast, you use RMM-DIIS all the way, so starting from the random numbers. But then we do quite a few non-self-consistent iterations before the mixer kicks in. And I will show you a little bit later what that means. So iterative refinement of the orbitals is preceded by the diagonalization of the full subspace. And after an optimization step, the refined orbitals are orthogonalized. So again, we have these order n to the power 3 operations in the full subspace, like in the Davidson. RMM-DIIS is approximately 1.5 times faster than the Bloch-Davidson, but less robust due to these problems with setting up good starting functions. So let's go back to our slightly disordered iron supercell and look at what the self-consistency cycle makes of it. For this longer cell, so the one that is shown here, this line you see here, these blue triangles, is a Davidson calculation. So this finishes for the largest cell in something like 25 iterations. Remember, this was conjugate gradient. So of course, instrumental in this is not that we use Davidson or that we use RMM. Instrumental in this is that we use density mixing to combat charge sloshing. So the mixer in this run, the mixing parameters have been optimized a little bit. So I've shown them here, and we'll get to optimizing those parameters a little later. Yeah, like I said, so instrumental is not that we use Davidson or RMM as opposed to conjugate gradient instrumental is that we use density mixing to get rid of this problem of charge sloshing. So now you could ask yourself, is it possible to use a direct optimization in combination with density mixing? And the answer is yes. If you use a direct optimizer, you might set L subrod to true. And in that case, an optimal search direction along the subspace rotational part of the gradient is constructed using density mixing. Now, this comes at a price. So to do this, the full subspace needs to be diagonalized multiple times for each and every direct optimization step. And like we said, this subspace diagonalization in the full subspace is costly, right? It scales, diagonalization scales cubically, and NB is the total number of bands. So this is the price that one pays. But then one can use a direct optimizer and still use density mixing to get rid of charge sloshing. And that is shown here, in fact. So we see that this is the black line, and the black triangles are for the elongated iron cell. And we see that this converges even faster than our Davidson. But that doesn't mean that we recommend that you use this on a per default basis because of the costs, right? So yes, you might shave off a few iterations, but the cost per iteration goes up substantially. So it's still better to stick to the self-consistency cycle. Yeah. So yes, the problem then, of course, if you so want, still means that density mixing is the solution. Sometimes you need to work a little bit on the mixer to have it perform optimally. So let's have a look at some of the output that the code produces during the electronic optimization. So we'll mainly look at a file called OSZICAR or standard out, because these give very concise information that will let you judge how your optimization process is doing, whether it's working. So the first things that we notice is that there's, we can distinguish our, we have here some 18 steps or 17 steps if you so want. This last one we'll skip. We have two distinct regions. So the first region where there's no numbers here, only the wave functions are optimized. So we see this is a Davidson algorithm running, and here, so here it starts from random orbitals and overlapping atomic charges, because we're starting from scratch. And for the first 4 steps, the charge density is kept fixed at the overlapping atomic charge density. And only the orbitals are optimized a few times. So we do this because starting from random numbers, if you would start mixing the charge density immediately after the orbitals have been partially optimized away from random numbers, then you would spoil the charge density. So the charge density stemming from the orbitals in the first few iterations is really crappy. So better to optimize the orbitals somewhat more with a fixed reasonable charge density approximation, which is overlapping atomic charges, before the mixer kicks in. So now this we do for Davidson, we do this 5 steps per default, something that one can change, but default is quite fine normally. For RMM, if we do RMM all the way, then we do 12 steps of that. And that has something to do with these. We need really quite good approximation to the initial orbitals. Otherwise, the RMM becomes unstable, might lose a state, like I mentioned before. So now what do all these numbers mean? Well, first of all, okay, this is the algorithm that is running. So this is Davidson, number of the iteration number, total energy. Does not necessarily have to go down in the self-consistency cycle. So this is okay, may go up, may go down. This is the change in the total energy from one step to the next. So the sign, like I said, does not have to be negative, but it should smoothly become smaller. Yeah, if your algorithm is running well and you're running so in exponential convergence, if you so want, then this needs to drop regularly by every so many steps. It needs to drop by an order of magnitude. This column is the change in the sum of the eigenvalues. This is how many times the Hamiltonian was applied to an orbital in this particular iteration. So this varies, right? Because we break off Davidson optimization on a block of orbitals. There's a few break-off criterions, right? So if the residual goes down quickly, then we don't need to iterate as deeply. And then we need to apply the Hamiltonian less often than in maybe some other step. So this is the sum of the norms of the residuals of the orbitals. So this needs to go down as well, right? The residuals need to become 0. And this here is after the density mixing starts, this is the root mean square change in the density from which the Hamiltonian is constructed. So density after mixing, if you so want, with respect to the previous step. And this really needs to go down. If you are converging, if the algorithm is converging like it should, this needs to decrease by an order of magnitude every so many steps, roughly speaking. Where depending on how strongly you mix, so for instance, the size of a mix might determine how many steps it will take before you drop by an order of magnitude. But if this gets stuck at some value, then you're no longer converging. Then it's simply doing something, even if this might become smaller, but then your system has stopped converging. Of course, okay, like I said, charge density fixed in the first few steps. Now, this is only when you start from scratch. If you start from a pre-converged set of wave functions from a WaveCar file, density mixing will start immediately. So a very similar file, of course, OSZICAR, a very similar picture you will get when you run a conjugate gradient calculation. These numbers mean slightly different things. So what we see here, of course, total energy, no, that remains the same. Change in the total energy. For a direct optimization that is working well, this needs to be negative. So the energy has to go down. This is different than what we saw for the direct optimization, for the self-consistency cycle. So this is no longer the change in the sum of eigenvalues, if you so want, per se. This is the expected change in the total energy based on the gradients and the step sizes. So this is the actual change. This is expected change. If you are in a quadratic energy landscape and gradients are accurate and all that kind of things, then these numbers need to be very close. So this is also a check whether you are in a region of the phase space where the approximation is good, where the conjugate gradient approximation is a good one. This is the number of times the Hamiltonian is applied to the orbitals. Now, this does not vary, not like in the self-consistency cycle. In every step, there's a certain number of times that the Hamiltonian is applied to the orbitals. RMS here is the norm of the gradient. This needs to go down, obviously. And this is the, so this ORT is the orthogonality of the gradient with respect to the previous search direction. And this needs to go down and become small. So if this for some reason does not happen, then your algorithm is in trouble. And the only thing that you really can play with in this case is the time parameter, so the time step that is taken. There's a little bit of additional information in the standard out if you run conjugate gradient. Most notably, this part here, the gradient. So there's 3 parts to the gradient. So this is a measure for the size of the gradient for the 3 parts. H is the out of subspace part. This is the subspace. So U is the subspace rotational part, and F is the gradient in the occupation numbers. For the orthogonality of the gradient with respect to the previous search direction, there's again 3 contributions that are written here. Yeah, this is more out of interest. So if you run a direct optimizer with density mixing, you will see that between each and every direct optimization step, there's a certain varying number of subspace rotations done. So each rod that you see here is one subspace diagonalization and rotation that is done to determine the optimal search direction for the subspace rotational gradient. Essentially using density mixing to get an optimal search search direction for this part of the gradient, this one, this one, the one that is responsible for charge sloshing. So yeah, depending on where you are within the convergence process, quite a few subspace rotations are done, and like I said, they are costly. So important INCAR tags, the most important one, if you so want, is the algo tag, by which you select an algorithm. So for normal, which is the default, you get block Davidson. For fast, you get the startup. So the steps with fixed density are done with block Davidson, and then the algorithm switches to RMM-DIIS. For very fast, it will use RMM-DIIS all the way. So those are the self-consistency cycle algorithms, if you so want. The direct minimization ones are algo is all, which is the conjugate gradient method, and algo is damped, which is a damped velocity friction algorithm. In case of the, I didn't mention this when we were looking at the OSZICAR files, but in case of the direct optimization algorithms, the fixed density phase, so the startup phase, is done using block Davidson. There's another way of selecting algorithms that's by means of the eAlgo tag, and this takes an integer. You can look at our wiki to see what you can set here. We do not recommend using this. This is the old way of specifying the optimization algorithms, so it's sort of legacy. And it allows a little bit more control, but these are the ones that we firmly support and recommend. So yes, you can reach other algorithms here, but we do not really recommend using them. So the number of startup steps with fixed charge density when you start from scratch is set by this NELM-DL. The maximum number of iterations is set by NELM. This is 60 by default and might not be enough. And then there's the minimum number of iterations that is done. You can also force the system to do a minimal number, even if EDIF is reached, continue until this minimum number is reached. That's NLmin. Another important tag is this one that determines iCharge, that determines how the initial charge density is constructed. By default, if you start from scratch, it is constructed out of overlapping atomic charges. If you start from a WaveCar file, it will use the density associated with those orbitals. So iStart tells the code whether to use the WaveCar file if present or not. By default, it will. So if it finds a WaveCar file, it will try to restart from it. And this is the time step used, the trial step size in the conjugate gradient algorithm, and the time step that is used in the damped velocity friction algorithm. So this is essentially the parameter that you have at hand to get these two direct optimizers to work. Especially for the damped velocity friction algorithm, choosing a time step that is not too large is critical, otherwise it might diverge even. The conjugate gradient method only uses this time as an for the initial trial step, and then it will try to automatically choose an appropriate time step. So that sort of is the end of the deterministic part of this talk, if you so want. Now comes the heuristical part. So tips and tricks and best practice, do's and don't, frequently asked questions. So essentially, I've tried to collect all kind of things that I think might be important, little bits of information that I hope will be useful to you, and try to phrase them as answers to frequently asked questions, if you so want. So let's get on with it. So what systems calculation are prone to show convergence issues? So like we saw, charge sloshing is one of the main reasons for convergence problems. So metallic and small gap systems in large simulation cells are prone to show trouble in convergence. And then there's another category, non-collinear magnetic systems. They are notoriously hard to converge, more so with GGA than LDA, and more so with meta-GGAs than with GGAs again. So meta-GGAs calculations in general tend to be somewhat more difficult to converge than calculations with other functionals. And especially this is the case when the structure has vacuum regions. So if you have a slab with a large vacuum, something like this, or a very open structure, or a molecule in a large box, those tend to be difficult to converge with meta-GGAs. And we are always looking for examples, by the way. So if you have trouble converging a certain system and you've run through all the tips and tricks that I will be sharing with you, then we are interested in knowing the particulars of this system. So by all means, do contact us in the forum if you run into those things. We will analyze them, try to improve the code and things like that. So next question, my calculation does not converge. What can or should I do? So the most important part is check your initial conditions. And it's sort of by order of importance. So many times something is wrong with the structure. Check your structure. Are the interatomic distances reasonable, and is the volume reasonable? So if you're very far away from something that is stable, yeah, it's hard for this. It's hard for the code to converge. That's a general rule. Yeah. So if you're running magnetic calculations, you need to specify initial magnetic moments. So there's this MACMOM tag by which you specify local moments. It's very important that you do so. I know the code will allow you not to do so. In that case, it will simply put one mu-Bohr of magnetization on each atomic site, whether it's a magnetic ion or not. Your system will be initialized as being ferromagnet, which it also might not be. So it's very important that you think about this if you do magnetic calculations and make a reasonable initial guess for your magnetic subsystem. So for meta-GGAs, initial conditions, you might restart them from pre-converged LDA or PBE calculations. That might definitely help. And then there's another thing, you should make sure that you include enough empty states. So possibly you need to include the number of bands in your calculation by setting M bands by hand. This is definitely often the case for systems that contain F electrons. We'll come back to this later, but if your highest lying state is occupied or partially occupied, this might very adversely affect convergence. Per default, use the Davidson and try to optimize the mixing parameters if necessary. That we'll get to in a bit. For magnetic systems, you might try linear mixing for the magnetic degrees of freedom, just a side point. Meta-GGAs in general, sometimes increasing L-max mix, which is the maximum L quantum number of the one-center charge density that is seen by the mixer. You might increase this from 2 to 4 or 6, depending on whether you have D electrons or F electrons in your system. And you might try mixing the kinetic energy density. This helps sometimes. Switch to conjugate gradient and optimize time if needed. The conjugate gradient algorithm sometimes found to be superior for non-collinear magnetic calculations. Definitely when including spin-orbit coupling. I've seen this many, many times. I can't give you a reason for it. I do not really understand the reason for it. But this is, this is the heuristic part of the talk. So this is why I mention it here. And for meta-GJs. So, and then possibly restart from a pre-converged WaveCar file. So, solving convergence problems, optimizing mixing parameters. So this is a sort of a scheme that tries to tell you how to go about this. I suppose that you already are using the Davidson. So if not, then use the Davidson. If this fails to converge, then we'll try to find out whether it's the charge, the density mixer, or something about the optimizer. So we'll fix the charge. Our charge is 12. We'll set the charge to overlapping atomic charges and then not update it, right? So it will keep the charges fixed at overlapping atomic charge densities. If the calculation doesn't converge, then the problem is not in the mixer. Yeah. So then we end up here. Yes, it says check your positions and contact us through the support forum. Well, I would like to add to this. Before that, you might try a different optimizer. So try the conjugate gradient, for instance. Yeah. So if fixing the charge density solves the problem of convergence, then obviously the problem has something to do with the performance of the mixer. So we switch back to I charges 2, which means start from atomic charge densities, but let the mixer work. And we try different settings for the mixing parameters. So the first one is this, A mix 01, B mix 001. That is line here. So the default was this blue one. Yeah, and this is this line here. So this is essentially straight mixing, but with a strongly reduced mixing coefficient. This A mix has gone from 0.4 to 0.1. So if that fails to converge, then try to mix more slowly here at low G vectors, at small G vectors, sorry. So that is done by increasing B mix and by decreasing A min. So you can always refer to this formula. That would be this green line. Of course, you can then you can force this to go down even more by changing A mix as well. So you end up with something here would be exceedingly cautious mixing. Yeah, and if either of those converges, then you use these settings. If that fails to converge, unfortunately, you end up here again. And in that case, contact us through support or try direct optimizer might help. But if you end up here through this route, chances are strong that it will get more and more difficult. Okay, so what are common mistakes? Well, like I said, unreasonable structure is a common mistake. Mistake in the sense of a mistake that you as a user can make. Magnetism, maybe you forgot to initialize the magnetic moments or you have initialized them badly. Not included enough orbitals. And the code will give a warning to this respect at the end. And will say, okay, your highest lying orbital is occupied or partially occupied. And if your system is not an insulator, then this is bad. Yeah. So these are, of course, all these are things that if this all doesn't work, all this stuff, then you should also look at this, obviously. So this is one that I like, and we get this quite a lot. This question: I ran the same calculation twice and I get different results. How can this be? Now, almost always something is different. Yeah, so the same. So it's not the same calculation. That's the most, absolutely by far the most common thing. So make a diff of the outcars. Look at really look at all the changes that those show. Are you using the same number of bands, same number of MPI ranks, parallelization setting? maybe not the same version of the code. Those mostly, in fact, it's due to a slight difference in the parallelization setting or the number of MPI ranks. This in turn might affect the number of bands. Yeah, you can have a look in the wiki to our section on parallelization settings to see the relationship between the number of bands the code takes and the number of MPI ranks and the way the job is parallelized. So there's a relationship between that. So sometimes running something on twice as many MPI processes will change the number of bands. And this will change your subspace. Yeah, and that means that you will no longer take the same optimization path through your parameter space, right? So a different number of bands will mean that your optimization will take a different path, and you might end up in a different local minimum. Because that is the reason why you get different results. You get different results because the total energy surface may show multiple minima and small changes. And in some pathological cases, even numerical noise may lead to a slightly different route that the optimizer takes, and you might end up in a slightly different, different minimum. So where is this common? You commonly see this for non-magnetic, non-collinear magnetic calculations. Magnetism generally, so two of the solutions that often exist is a non-magnetic one and a magnetic one. So those would be two local minima already. LDA plus U is prone to this. Question then often comes, so what is the correct one? Now, well, both minima are correct in the sense that they're stable DFT solutions. One will be lower in total energy than the other. So one will be a metastable or a local minima, the other will be the global minima. Do you know that you have found the global minimum? It's very difficult because there might be another one, if you so want, that is lower in energy that you haven't found yet, so there's no guarantee. The total energy surface is many times not as unbehaved or badly behaved as that, but there's nothing particular about a certain minimum that says, okay, I am the global minimum, obviously, right? So how should I approach hybrid functional calculations? You use block Davidson with adaptively compressed exchange. That is set by this tag. That is a very good first try, or use a conjugate gradient method or the damped velocity friction algorithm. So either this block Davidson with adaptively compressed exchange or a direct optimization algorithm. Possibly in the latter case with L subrod is true if charge sloshing turns out to be a problem. This is less often the case with hybrid functional calculations because they tend to have a larger gap. So charge sloshing is less of a problem in many cases. And start with the DFT calculation and restart the hybrid functional calculation from the waveguard. That's not necessarily a trick to reach convergence, but you might reach it faster. It might help to shave off a few costly iterations. What is the role of symmetry in this? Now, this is a complicated question. Using symmetry, so symmetrizing the charge density, can effectively reduce charge sloshing. If you think back to the very first example of charge sloshing, you had these two sides that were identical, and two electrons were hopping from one to the other and back and forth and back and forth, whereas you would have liked one on one and one on the other. Now, if you would symmetrize the charge density, you would end up with one on one and one on the other, right? So this, using symmetry can effectively reduce charge sloshing, but unfortunately, it can also block the way to the true ground state. The symmetry of, for instance, a magnetic subsystem may be lower than the crystalline one, right? So symmetry routines look at what you specify for Magnum for the initial magnetic moments to check whether a certain symmetry operation is allowed. Yeah. But what you will find in the end is somehow determined by the symmetry of your initial moments then, right? So, and that might not be the ground state. So it might be impossible, for instance, if you initialize your system as being a ferromagnet, you will not find an anti-ferromagnetic solution. The symmetry symmetrizer will symmetrize that away. And it might be that your electronic optimizer is trying to reach that, right? So it's trying to change your orbitals in such a way that it will reflect an anti-ferromagnet. Then the charge density is recomputed. The symmetrizer comes and floops, throws away all these little changes towards an antiferromagnet. So it might, in fact, you might in fact get stuck in your optimization. Convergence might halt because of this. Same thing goes for orbital ordering. So the orbitals those are a little bit esoteric, but the orbital ordering, so which orbitals are occupied at certain sites might might break the symmetry of the crystal, if you so want. Yeah. And then there's another an important one, and that is the finite numerical accuracy. So the atoms are they are at certain positions with respect to the numerical grids that we use to represent the density and so on. And there's always a slight egg box effect in this. Now, so it might be that due to this finite numerical accuracy, due to these egg box effects, the action of the Hamiltonian has a lower symmetry than the symmetrized density. Yeah. So again, the residual, the action of the Hamiltonian, the residual, try to move the wave functions into a direction that breaks the symmetry. Then you compute the density that gets symmetrized, and then so this tendency gets symmetrized away. In the next step, the whole thing starts all over again. Refinement of the orbitals tries to break the symmetry again. Then charge density is mixed, whoop, and it is thrown away, and the thing doesn't reach convergence because of this. So combination of finite numerical accuracy and symmetry might actually effectively hinder convergence. So are there limits to the degree of convergence I may expect to reach? Obviously, yes. We have addressed already a few points. Like I said, GGAs are harder to converge than LDA. Meta GGA is even harder to converge than GGA. This is just heuristically speaking the case. Another thing that's easily understood, system size, right? More general, the number of degrees of freedom. So I might be able to converge a primitive cell with 2 atoms to 10 to the minus 8 EV, but if I build a supercell out of this, I don't know, a 10 by 10 by 10 supercell, so 1,000 times larger cell, can I still honestly expect to be able to converge this to E diff is 10 to the minus 8? No, this will be more difficult. And the same thing we already addressed, right, was this finite numerical accuracy. So there will be at some point the accuracy, the errors that we make in certain operations will kick in, and we will no longer have for instance, in a direct optimizer, we'll no longer have an accurate enough gradient to follow. So yeah. Yes, so this there are limits to the degree of convergence you may expect to reach. You should always think about the level of convergence that you need to reach, and not try to go to absolute convergence if you so want. So one other thing, what should I watch out for? Now, the most general and the most important answer maybe is check for convergence. So the code will tell you when it has not converged within this maximum number of steps, and you should heed this. And so if you see that your calculation If you have not set NELM, it will be 60. This is the default. If you see in your OSZICAR file that the last iteration is iteration 60, then you should worry. This is in many cases has not reached the convergence threshold. Might still be sufficient, obviously, it depends on what you have set for eDiff, but check for it. And then one other thing is very important, watch out for spurious convergence. It might happen that from one step to the next, especially if you're not converging exponentially, that from one step to the next, you might coincidentally make a very small change to the total energy. And the system will say, okay, I'm converged. If you would have continued, the next step might have been much larger. Next change in the total energy. So you're still definitely not converged. This is what I call spurious convergence. So you should really watch whether the last, so it breaks off because it hits a certain change in the total energy, and this should be in line with the recent history of this property. Okay, well, that brings me to the end. I hope the first part of the talk has not been too confusing, and I'm sure that in the heuristical part, I probably failed to cover a lot of questions that you might still have. And with this, I thank you for your attention.
Thank you, everybody.
Ciao, ciao.